Alrighty, everyone. This is going to be our first venture into video clickers. Now, obviously, you will not be able to use your clickers. I won't be able to tell how many people got things right. Some of these slides actually do have results from last year's class, so I will at least be able to show what the typical answers are for a Fundamental Physics 1 class, and try to explain why the popular wrong selections were wrong. The way I would like you to do this is when I put up a question and after I read the selections, please pause your video. Pause your video until you make your selection. And then after you make your selection, play the video again and I will immediately put up the answer. Okay, so this basically will save some recording time. I won't be just standing around hemming and hawing waiting for everybody to get their clickers done, because basically you're doing this one at a time. So anyway, without any further ado, let's go on. Okay, 70-kilogram astronaut is performing a spacewalk at a distance of 225 miles above the Earth's surface. What is the Earth's approximate gravitational field strength at that location? Okay, this is actually from a previous chapter somewhat, but it's something you should be able to answer. Answer A is 9.8 newtons per kilogram. Answer B is 8.7 newtons per kilogram. Answer C is 1.6 newtons per kilogram. Answer D is close to 0, or answer E is exactly 0. Okay, pause your video and make your selection. All right, the answer is 3, 2, 1. Oh, where is there we go. There's the little check mark. Okay, the correct answer is 8.7. At the surface of the Earth, it's 9.8. So that is the normal gravitational field strength. 8.7 is a little bit less. So basically 225 miles above the Earth's surface is going to have less gravity, but not that much less, because the Earth is about 4,000 miles in radius, so you would have to go probably 1,000 to 2,000 miles to really reduce it to almost half or so. So this one is too small. Close to 0, exactly 0. No, none of those are correct. In fact, there is no such thing as zero gravity, although in free fall you can feel as though you're in zero gravity. Okay, so the answer basically, 6% of the Earth's radius above the surface, and 1 over r squared at that location is about 12% less than at the surface. So if you wanted to do the math, you could do it that way, but you should be able to just kind of figure it out. Okay, next question. Assuming no air drag, which of the following situations is a ball in free fall? A, while a ball is in the process of being thrown upward, but still being held. So in other words, before it leaves my hand and I'm throwing it upward. B, while a ball is moving upward after having been released from my hand. C, as a ball hits the ground. Or D, none of the above. Okay, pause your recording and answer the question. Alrighty, 3, 2, 1. All right, the most popular answer is B, and that is the correct answer. Okay, while a ball is moving upward after having been released. Now, you might think, now, wait a minute. How can something be falling if it's moving upward? And basically, the word free fall just means that the only net force that is acting on the object is gravity. And the force of gravity is downward. But basically, moving upward, you are decelerating. You're slowing down on the way up. And so you're still under the influence of gravity. But the influence of the net force is in the opposite direction that you are moving. Okay, so there is such a thing as falling up, as I said in class a couple weeks ago. Is it okay to ignore the air for stationary objects? Is it okay to ignore the air for stationary objects? I assume what they mean here is the force of the air. A, no, without air there would be no gravity. Or B, yes, the air, if present, pushes down on objects, but not significantly. Or C, yes, the air, if present, pushes equally all around an object. Or D, yes, the air, if present, doesn't push objects up or down, only side to side. Okay, pause the video and make your answer. Alrighty, 3, 2, 1. All right, the most popular answer for this one was D. However, I did actually change the selections from last year because I thought that the wording was a little too confusing. The actual answer is C. The air present pushes equally all around an object. So that's why you don't notice the 15 pounds per square inch of air pressure because it is pushing all around you. We mentioned that if you can somehow reduce the air pressure on one side of an object, you would have it adhering to a surface. So that's kind of what a suction cup does. A suction cup reduces the air pressure on one side of the object, and so basically the air pressure on the other side of the suction cup presses it to the smooth surface that it is adhering to. All right, next one. A ball falls under the influence of gravity as illustrated in the time-lapse picture on the right. When does the ball achieve a constant velocity? Okay, remember now we are ignoring air resistance. When does the ball achieve a constant velocity? A, at the moment it is released at 0.0 seconds, or B, a tenth of a second after being released, or C, around 6/10 of a second after being released, or D, the ball never achieves a constant velocity prior to hitting the ground. Okay, pause your video and make your answer. Alrighty, 3, 2, 1. And the most popular answer was D, the ball never achieves a constant velocity prior to hitting the ground. And that is correct. And again, the reason that is correct is because when the ball is falling, there is only one net force, and that is gravity. And when there's a net force, it means there's a constant change in motion. So you never get a constant velocity when you get a constant change in velocity, do you? Because if a velocity is constantly changing, it means the velocity can't stay the same. Okay, so remember the word constant means to stay the same. And in this case, with nothing but gravity acting, you're always speeding up. And this is why falling is a dangerous thing and should be avoided. What is the direction of the gravitational force on a ball due to the Earth? A, downward, B, toward the south, C, horizontal, D, depends on where the ball is, or E, depends on which way the ball is moving. Okay, so what we're talking about here is a ball that is close to the surface of the Earth. Okay, close to the surface of the Earth, not somewhere halfway to the moon or anything. Alrighty, make your answer. Pause the video, make your answer, and we will see what the selection is. Alrighty, going once, going twice, going 3 times. And the most popular answer was A, thank goodness, and that is correct. That is downward. In fact, that defines up and down. Up and down, and we grow up in our lives knowing that there's an up and there's a down, but we rarely think of what that means. And what that means is up is in the direction opposite of the force of gravity, and down is the direction toward the force of gravity. That's why, for example, astronauts in space who are seem to be in the absence of gravity. I'll see if I can explain that in a couple of days. Seem to have trouble figuring out what is up and down. All directions are equal. But when you're in the gravitational field and you're experiencing that gravitational field in the way we do, down is basically toward the center of the Earth or the force of gravity. Okay, so the gravitational force due to Earth is toward the Earth's center, whether the ball's at rest, moving downward or moving upward. Okay, a ball is thrown downward and falls under the influence of gravity, as illustrated in the time-lapse picture to the right. When does the ball achieve a constant velocity? A, at the moment it's released, B, 0.1 seconds after being released, C, around 0.4 seconds, or D, the ball never achieves a constant velocity prior to hitting the ground. This seems a little bit like a rerun to me, but answer the question and we'll see what the answer is. Alrighty, pause the video, answer the question. 3, 2, 1, and thankfully, Just about everybody got it right. The ball never achieves a constant velocity prior to hitting the ground. Again, if gravity is the only uh, force acting, as it is in free fall, then it's always speeding up on the way down, okay, or it's always increasing its downward velocity, I should say. Okay, a ball is thrown upward. Okay, it starts here, goes up, and then falls straight down. It's a little hard to tell from this picture, but 0 seconds is here. So this is the first image. It goes up, comes to a stop for just a smidgen of an instant, and then starts falling back down again. Okay, when does the ball achieve a constant velocity? A, at the moment it is released, 0.0 seconds. B, at the top of its motion, around 0.3 seconds. C, around 0.9 seconds. Or D, the ball never achieves a constant velocity prior to hitting the ground. Okay, pause your video and answer the question, please. Alrighty, going once, going twice, going 3 times. And yay, the answer again is D. Okay. The easiest way to get tricked by this is at the top of its motion, around 0.3 seconds. In fact, if I had worded this question that at the top of its motion where its velocity is 0, I bet a lot more people would have chosen B, because it's really easy to get confused by that. So at the top of its flight, yes, it is at 0 velocity, and it is technically, quote, stationary, unquote, but that does not mean it's not changing, because just a little bit before that moment, it is moving upward, and just a little bit after that moment is moving downward. And so therefore, the word constant would not be applicable in that sense. Okay, so D is the correct answer. All right, I drop a 2-kilogram ball from rest. If there is no air resistance, what is the net force acting on the ball as it falls? Okay, and we're using the approximation of 10 newtons per kilogram as the gravitational field strength. Okay, so what is the net force acting on the ball as it falls? A, 0, B, 10 newtons upward, C, 10 newtons downward, D, 20 newtons upward, E, 20 newtons downward, and F, none of the above. Okay, pause your video, make your selection. Alrighty, 3, 2, 1, let's get the answer. And E was the most popular answer because it is in fact the correct one. Okay, you multiply 2 kilograms, put that in for M, by 10 newtons per kilogram. Basically, this G is just telling you how many newtons of force there are for every single kilogram of mass in the object, and that tells you the strength of gravity. Now, of course, if this were a different planet with a different mass and a different radius, this G, this number here, this field strength would be different. Okay, so for example, if you had a planet where the field strength was 5 newtons per kilogram, then C would have been the correct answer. All right, let's go on to the next one. I drop a 2-kilogram ball from rest. How fast is it going? 0.5 seconds later, half a second later. All right, it starts out at 0, in other words, and half a second later, how fast is it going? A, about 20 meters per second, B, about 15 meters per second, C, about 10 meters per second, D, about 5 meters per second, or E, 0. Okay, pause your video and try to answer this question. Take your time. All right, let's look at the answer. 3, 2, 1. All right, about 5 meters per second. Okay, that's because in addition to being 10 newtons per kilogram, this is also the acceleration of gravity, as we showed in the previous video, which means you speed up by 10 meters per second each second. Okay, so the acceleration of gravity is 10 meters per second, and that means in a half a second, you're going to speed up half of 10 meters per second because you've only had half a second to fall. So 5 meters per second would be the correct answer. Okay, actually we are just about out of our 15 minutes, so I'm going to stop the recording here, and you can watch part 2 of the clickers, which is only a few more questions, and then we'll be done.